Hi everyone, my name is Kwan Nguyen. I'm a power system engineer at the Pacific Northwest National Laboratory. Today I'm going to present our work on EMS and DMS integration of the coordinated real-time subtransmission vulva control tool under high DER penetration. About the background of this work, increasing DER generation requires new methods and tools that can increase system operational efficiency and reliability at distribution level. DER also can affect the operation at the sub-transmission and transmission levels as well. Because of that, research has been focusing on closing the gap between T&D operation. Recently, PNL developed a new tool, which is the Coordinated Real-Time Subtransmission Vulva Control Tool, or CReST-VCT. It is an optimal operational tool that optimizes the use of all reactive power resources at subtransmission and distribution levels. In this work, we develop a generalized design framework for CReST-VCT and potentially other T&D tools in EMS and DMS to enable high DER penetration. We also provide a thorough analysis on potential performance and security issues. Finally, we give at a high level an example of implementing the distribution part of CReST-VCT in an open source platform called GridAppsD, which is also developed by PNL. This figure shows the overall operating architecture of CReST-VCT. CReST-VCT optimizes the use of all reactive power resources in subtransmission system and distribution systems by solving two optimization problems in subtransmission and distribution system. And it relies heavily on the communication between bidirectional communication between EMS and DMS. And more information about CReST-VCT can be found in one of the references in our paper. The key path at the distribution level installed in DMS of CReST-VCT is called the voltage load sensitivity matrix based vulva control application. And this application, together with other distribution applications, can be installed in a platform called GridAppsD. And here is the overall architecture of GridAppsD. It has built-in features like power flow, state of estimation. It has multiple communication blocks like this. And also it has built-in distribution simulators like GridLabD and OpenGTS. And now I'm going to talk about how this vulva control tool in DMS can coordinate with the transmission path of CReST-VCT installed in EMS. So every 5 minutes, this transmission part of CReST-VCT will send an operating point for the distribution system through these communication blocks to the vulva control application. And in the second step, this vulva control application will solve its own optimization problem and determine the operating point for all of the DER and other reactive power resource in distribution system. And then it sends this control, this operating points to DER and other reactive power resources in distribution system through this control block, these communication blocks. And finally, this control application will estimate the operating limits of distribution system in the next 5-minute interval and send it back to the EMS. Regarding performance analysis, we have to talk about first communication variation. So communication latency and bandwidth can introduce variation to the system. This latency and bandwidth, they vary with the chosen protocols and layer of the communication network. Second, communication delay effects can have negative impacts on the performance of CReST-VCT. And if we have less communication delays, it means that the optimization solution will reach the DER and other reactive power resources faster, which overall improve the performance of CReST-VCT. Regarding scalability of CReST-VCT, because CReST-VCT assumes two-way communications between EMS and DMS, so if we use a centralized control, then it will reach a scalability limit by the 5-minute interval of CReST-VCT operation. Because of that, we suggest distribution operators to adopt distributed control approaches to control DER locally with less communication requirements to improve the scalability of CReST-VCT. Finally, regarding security risk, the operation of CReST-VCT can be threatened by because of the digital communication with various communication protocols and control interfaces. These protocols and interfaces will pose security risks to the system. And also the security risk also can be resolved from large number of third-party devices in the system. In conclusion, we believe that the proposed design framework and implementation of CReST-VCT in GridApps-D can be applied to other distribution applications as well. And we suggest utilities and vendors to consider communication variation and delay, scalability, and security for any type of EMS, DMS application related to DER devices. Regarding GridApps-D, we strongly suggest distribution system operator, vendors, and distribution system developers to consider GridApps-D because of the following advantages. First, GridApps-D is a robust open source development and testing tools for advanced DMS applications that heavily relies on communication infrastructure. Second, it has built-in distribution system simulation capabilities. And finally, because of its standardized architecture, GridApps-D can be considered as a reference architecture for multiple industry application adoptions. Thank you.